What is the derivative? It's a function that tells you the slope of the line tangent to the curve at every point. Slope meaning the steepness of the line, how slanted it is, and the tangent line meaning the line that touches the curve only at one point. Every point on your graph, therefore, has a little tangent line. In short, a curve function will not have a single slope because it is not straight, but rather it will have multiple slopes respective to each point. And the derivative, denoted as f prime x, tells you the value of these multiple slopes. So, if the derivative is supposed to tell you the slope at each little tangent line, how can we know that slope if we only know one point at each tangent line? And as we learned from basic algebra, we need 2 points to get a slope. For now, we don't know how to do that yet. But we can know how by integrating things that we know. Okay, so if you want to know the slope of this tangent line at any point, let's say x, we can start with the good old slope of the straight line between 2 points. Pick a second point somewhere in the curve and draw a straight line through. Now we have a secant line, a line that touches the curve at 2 or more points. And we know how to find the slope of a straight line with the good old-fashioned slope formula, aka rise over run. So before moving on to apply the formula, let's label the points. If the second point is some distance away horizontally, let's call the distance h, then this point has an x-coordinate of x plus h. So the first point will have an x-coordinate of x and a y-coordinate of f of x, or basically the value of y when x is x, while the second point will have an x-coordinate of x plus h and a y-coordinate of f of x plus h, again meaning the value of y when x is x plus h. Now, we finally have 2 points, which is great because we can use these 2 points in the slope formula, which we all know very well. Okay, so to recall, the slope is equal to the vertical change over the horizontal change, or the second y minus the first y, over the second x minus the first x. Plugging in the coordinates of the 2 points we have to this formula, we have f of x plus h minus f of x over x plus h minus x, simplifying to f of x plus h minus f of x over h. So again, this tells us the slope of the secant line. Actually, we would be done if this graph was linear. This slope that we found would be true everywhere, but we don't have that. We have a curved graph. And for the curved graph, again, since there is no definite straight line, thus no constant slope, our basis to get the slope at each point would be its tangent line. Take note that a tangent line meets the curve at one point only, so our goal here then with the secant line is to somehow make these 2 points 1. We can do this by closing in on x by narrowing h to 0. We adjust the slope until the horizontal distance gets infinitely smaller and smaller. The smaller it is, the more accurate the slope is, the more accurate the derivative is. Now, by what concept of calculus can we mathematically express this? That's right, limit. We can take the limit of this function as h. The horizontal distance between the 2 points approaches 0. As the 2 points come closer and closer, what does the function, the slope, approach? Basically, it will tell us at what slope of the secant line passing through x and f of x, it will be a tangent line which solves our problem. And so, the limit of the function is the slope of the tangent line, and that limit defines also the derivative. This is finally the definition of the derivative when that limit exists. This notation is read as f prime of x, which just means the derivative of f of x. Also, I should say that the tangent line slope can be always changing in different places. It's very variable. That's why the derivative itself is a function. You can get the tangent line slope at a given point x by plugging it in the formula. Moving on, let's try this example. We are given a function equal to x squared plus 5x, and we are asked to find f prime 2 and f prime negative 1, meaning the derivative of the function when x is equal to 2 and when x is equal to negative 1. In a more visual sense, it is the slope of these two tangent lines, the orange and purple. And earlier we defined the derivative of a function given point x and f of x as the limit of f of x plus h minus f of x all over h as h approaches 0. As we are given x is 2 and negative 1, we can now calculate the derivative of the function at these points. First, we have x equals 2. Plugging in the 2 to the derivative function, we have f prime 2 is equal to the limit of f of h plus 2 minus f of 2 all over h as h approaches 0. This simply means the value of the function when x is h plus 2 and when x is 2. So in the same way, we plug in h plus 2 and 2 to f of x, the original function. Now, we have this expression. Finally, after a series of simplifying, we end up with the limit of h plus 9 as h approaches 0. Then, by the substitution method of limits, we get a value of 9 for f prime 2. This means that the slope of this orange tangent line is 9. So this somehow is the general process of getting the derivative of a function with respect to x. Moving on to the second question, we do the same process. By substituting negative 1 to the derivative function, we get this expression. And by substituting h minus 1 and negative 1 to f of x, we get the expressions for f of h minus 1 and f of negative 1. And plug them into the equation. Further simplifying, we find that f prime negative 1 is 3, which similarly means the slope of this purple tangent line is 3. However, a more practical way to think of it is that the derivative gives you the rate of change at any instance, as rate of change is simply how fast a variable changes with respect to another variable, aka the ratio between the changes in two variables, aka the slope. It is therefore a function for the instantaneous rate of change at each point. For instance, you can apply it in something like physics, where if you're looking at something moving in time, the position changing in time, let's say an object free falling. A curved graph would mean that the slope is always changing, which in this case is the velocity. The velocity is changing and not constant because there's an acceleration due to gravity, whereas if you had a straight line graph, the slope would be the same everywhere because the velocity is not changing because there's no acceleration, which is therefore not practical to use when dealing with gravity. In other cases, however, the rate of change is measured with respect to 2 points, in which case you can form a line segment. And as I mentioned earlier, you can regularly calculate the slope of a function by the good old slope formula rise over run, assuming you have 2 points, aka an interval. This is called the average rate of change, in which case derivatives is not much applied. So in the same way that the instantaneous rate of change or the derivative at a point is equal to the slope of the tangent line at that point, the average rate of change over an interval is equal to the slope of the secant line that connects the endpoints of the interval. To sum it up, instantaneous is relative to a point, while average is relative to an interval. Or even shorter, the instantaneous rate of change is an extreme case of average rate of change where interval is 0. To further understand this, let's consider the free-falling object scenario earlier. Suppose the ice cream fell from the sky wherein its height in feet after t seconds is given by the function h of t is equal to 16t squared plus 96t. First, we are asked its average velocity in the first 3 seconds. Next, we are asked exactly how fast it is going at t equals 1 second, its exact velocity. Okay, let's first identify the variables and look at the problem in the context of rates of change. We know that to get the height of the ice cream, we will need to input after how long it has fell, which is t. So x, the independent variable in this case, is t, while f of x, the dependent variable, is the height, h of t. For the first question, we also know that the average velocity is defined as a change in the displacement over change in time. In this case, delta h of t over delta t, which is the average rate of change of h of t. Let's then write the general definition of the average rate of change in the context of average velocity. Doing this, we have the difference between the two heights or the height interval over the time interval. The time interval in this problem is between t is equal to 0 and t is equal to 3, as it states in the first 3 seconds. So plugging in 0 to the height function, we get h times 0 is 0, and h times 3 is 144. Finally, after these values, we get that the average velocity for the first 3 seconds is 48 feet per second. Now, the second question is similar. We are looking for the velocity or the rate of change. However, we are only given one value of t, 1 point, and we are asked to find the exact velocity at that point. So, what concept can we use as we deal with the point? That's right, the instantaneous rate of change. Again, looking at this definition in the context of the problem, x will be t and f of x will be h of t. Then, plugging in t is equal to 1 second to the equation, we have the following expression. Further simplifying, we end up with a limit of negative 16h plus 64, which by substitution is 64. So, the exact velocity of the ice cream at t is equal to 1 second is 64 feet per second. Notice that how we calculate derivatives is somehow a long process. Based from the mathematical expression of the derivative, we can obtain extreme cases and establish derivative rules that will simplify it into easier individual processes. The following are only some of the many derivative rules. The constant rule basically states that the derivative of any constant is 0. For example, the derivative of f of x equals 5 at any point is 0. Next, we have the constant multiple rule, which tells us that if a constant can be factored from a function, its derivative is equal to the derivative of the factored function times the constant. For instance, if g of x is given by 16x squared minus 8x, wherein you can factor 8 out, then g prime x is 8 times the derivative of 2x squared minus 1. Third is the power rule. It states that if f of x is equal to x raised to n, then f of prime x is equal to nx raised to n minus 1. An example we have here is when f of x is equal to x cubed. The derivative of this function is equal to 3, the exponent, times x to the power of 3 minus 1. Lastly, we have the sum and difference rule. Basically, it tells us that the derivative of a function is equal to the sum or difference of the derivative of its terms, its mini-functions. So, applying this here, the derivative of square root of x plus 7x is the sum of derivatives of square root of x and 7x. If we apply these rules to the function earlier, we can first use the sum and difference rule, and then the constant rule, and finally the power rule. By this process, we get a much faster solution, yet the same answer. Aside from physics, another practical application of derivatives is in economics. In economics, the instantaneous rate of change of the cost function is called the marginal cost, or the cost added from producing one additional unit of a product or service. So if c of x is the cost function, then the marginal cost is c prime x. But why can't we use simple rates of change in economics? That's right, because graphs are curves wherein slopes vary. So for instance, we are given the cost in dollars of producing X units of a certain commodity is C of X equals 5 plus square root of X dollars. We are asked to find the marginal cost when production level is 100. As I mentioned earlier, marginal cost pertains to the instantaneous rate of change. So we have the derivative of C of X. By the derivative rules we studied earlier, we can simply process by first using the sum and product rule, and then the constant rule, and finally the power rule. Take note that the power rule works also for radicals, aka fraction exponents. Then, finally, we get the derivative function 1 over 2 square root of x. Plugging in x equals 100, we get a value of 0.05. This means that the cost added from producing one additional unit of the commodity when the production level is 100 is $0.05. Quick recap. What have we learned today? The derivative function of f of x with respect to x is the slope of the tangent line or the instantaneous rate of change mathematically expressed as the limit of f of x plus h minus f of x all over h as h approaches 0. Rates of change, on the other hand, come in two ways, average and instantaneous, wherein average is the slope for the secant line and instantaneous is for the tangent. To simplify the process of solving for the derivative rules are established such as constant multiple, power, and sum and difference rules. Lastly, we learned that the rates of change have a wide range of practical applications, velocity and marginal cost, and the like, for instance.